A universe made of almost nothing. Why is the universe so empty? If it began as an unimaginably dense, blazing fireball packed with energy and particles, how did it relax into an ocean of almost pure nothing, with just a few tiny islands of matter, like our planet and our star? Look around you for a moment. The walls, the floor, the screen in front of you, the air you are breathing. Everything feels solid, crowded, full. In a single breath of air, there are around 10 to the power of 25 molecules. That is a 1 with 25 zeros after it. But while our immediate surroundings feel rich with stuff, the average patch of space between galaxies contains about one lonely atom in an entire cubic meter. 1. For that same volume in this room, we are talking about numbers so huge, they are almost impossible to picture. This means that if we zoom out, if we stop thinking in terms of rooms and cities and even planets, the universe looks very different from our intuition. Astronomers have spent decades mapping the sky, turning faint smudges of light into three-dimensional positions, and when they connect the dots, a pattern emerges. Galaxies are not sprinkled evenly. They trace out a vast cosmic web, thin filaments and sheets of galaxies and clusters, wrapped around enormous, silent voids. Some of these voids span hundreds of millions of light years. The Boat's void is so large that if our entire Milky Way were placed at its center, we could travel for hundreds of millions of years at the speed of light and still see almost nothing. In the hunt for alien life, we keep building bigger telescopes, more sensitive detectors, more ambitious surveys. We expect more planets, more stars, more signals. But while the catalogs do expand, something else keeps growing faster: the darkness between the islands of matter. We discover new exoplanets, yet we also discover that most of the cosmic volume is empty, that most galaxies are isolated by gulfs of pure space, and that even light takes billions of years to cross the gaps. It should be noted that this is not just visually dramatic, it is emotionally strange. Why does a universe so vast feel so deserted? So, let's begin with that paradox. If the cosmos started out hot, dense, and uniform, why has it ended up as a structure where matter is rare, life is rarer, and contact between distant civilizations might be nearly impossible? Is this emptiness a clue that intelligent life is vanishingly unlikely, or is it precisely the kind of universe required for any life at all to exist? Optimistically speaking, the voids might even be part of the reason we are here to ask the question. So it's time to find out the truth about why the universe is so empty, and what that emptiness really means for us. Why cosmic emptiness matters more than you think. If the universe is mostly nothing, why should we care? There are few questions that cut more deeply into both science and philosophy than this one. Because this emptiness is not just a bit of trivia about big distances. It is the stage, the director, and half the script. The average cubic meter of intergalactic space holds about one lonely atom. That near-perfect vacuum decides how galaxies form, how stars ignite, how they die, and whether the heavy elements needed for complex chemistry and life ever appear at all. This means the void is not a background detail, it is a main character. Think about our own situation. We evolved on a dense little rock, with oceans, mountains, and a thick atmosphere inside a bright, crowded band of the Milky Way. To us, a normal night sky is full of stars, but while our senses insist that fullness is the rule, the universe disagrees. On cosmic scales, emptiness is normal. Our planet, our star, even our entire galaxy, are rare islands of matter floating in a vast, silent sea. It should be noted that this makes our intuition almost useless once we zoom out, and that sea is getting bigger. Dark energy, the mysterious component making up about 68% of the universe, is accelerating the expansion of space itself. Galaxies are not just drifting apart, the fabric between them is stretching faster and faster. Give it enough time and distant galaxies will slip beyond our observable horizon. Future astronomers, living on some distant Earth-like world, may look out and see only their local group, with no evidence of the cosmic web at all. Their universe will appear smaller, emptier, and far more lonely. Now connect this to another puzzle. In the hunt for alien life, we often hear a simple argument: hundreds of billions of galaxies, billions of stars in each, planets everywhere. So where is everybody? This is the Fermi paradox in one sentence. But while we imagine a crowded, buzzing cosmos, the reality is that most of space is not just uninhabited, it is almost unimaginably empty. Could that sheer emptiness be part of the answer to why the universe feels so silent? Optimistically speaking, there is a twist. What if an almost empty universe is exactly what you need to get complexity at all? So, let's begin a narrowing journey from the largest scales of the cosmic web down to galaxies, solar systems, and even the space inside atoms. At every level, we will find that nothingness dominates, and that the tiny fraction of something behaves the way it does only because the rest is void. So it's time to find out the truth about how deep this emptiness really goes, and what we discover when we fall into it. Zooming out, the cosmic web and its giant voids, so if almost everything is nothing, what does that actually look like on the largest scales of the universe? When astronomers tried to answer that, they did something bold. They started to map the cosmos in 3D. Instead of just taking pretty images of the sky, large surveys measure the redshift of hundreds of thousands of galaxies. Redshift tells us how fast a galaxy is receding as the universe expands, which, in turn, tells us how far away it is. This means each fuzzy smudge becomes a precise point in space. Connect millions of those points, and a flat night sky suddenly turns into a vast, three-dimensional structure. But while you might expect those galaxies to be sprinkled evenly, like sugar on a table, the data shows something very different. They form a pattern, long, thread-like filaments, broad, gauzy sheets, dense knots where many filaments intersect, lighting up as massive clusters of galaxies, and in between these structures, huge, dark gaps. The result is what we now call the cosmic web. The cosmic web is not a poetic metaphor, it is the actual largest-scale architecture of the universe. Most of the galaxies, stars, and potentially habitable planets live along these filaments and clusters, where gravity has pulled matter together. It should be noted that these bright regions, impressive as they look, occupy only a small fraction of all the available volume. Most of space is taken up by the opposite of structure, enormous underdense regions, called cosmic voids. How big are these voids? Let's take a concrete example. The Boats void. When it was discovered, it looked like a hole in the universe itself. It spans roughly 330 million light-years across. Inside that volume, we find only a few dozen galaxies where statistically, we might expect thousands. For comparison, our Milky Way is about 100,000 light-years in diameter. You could line up more than 3,000 Milky Ways across the Boats void and still spend almost all of that journey flying through emptiness. Pattern interrupt. Imagine every star you have ever heard of, every exoplanet we discuss in the hunt for alien life, compressed into a thin, ghostly web with vast black oceans on every side. That is our true cosmic address. So why does matter arrange itself this way? Computer simulations like Millennium and Illustris start with tiny quantum fluctuations in the early universe and let gravity, dark matter, and cosmic expansion do their work. Optimistically speaking, if our theories are right, the result should resemble reality, and it does. The same filaments, the same clusters, the same giant voids emerge naturally. So, let's begin to accept an unsettling conclusion. This near emptiness is not an accident. It is what the fundamental physics of our universe prefers. In the next step down in scale, we will dive from these filaments into a single galaxy and see that even there, the rule of emptiness still holds. Gravity's sculpting, how the universe learned to be sparse. So, if the cosmic web is real, we have to ask, how did the universe learn to be so sparse in the first place? Because it did not start that way. Right after the Big Bang, everything was a hot, glowing plasma. No galaxies, no planets, no stars. Just a nearly uniform fog of particles and light, the same in every direction to about 1 part in 100,000. Those tiny bumps in density, those almost invisible overdensities and underdensities, were seeded by quantum fluctuations stretched to cosmic scales. It should be noted that without those microscopic imperfections, there would be no structure at all. So, let's begin with that fragile imbalance. Imagine two regions in this early plasma. One has just a fraction more matter than average, the other a fraction less. Gravity is weak, but it is patient. The slightly denser patch pulls a bit more strongly, slowing its expansion, drawing in extra material. The slightly emptier patch does the opposite. It expands a little faster, losing matter to its surroundings. Over millions of years, that tiny difference is amplified again and again. This means the rich get richer in terms of gravity. The growing overdensities stretch into sheets and filaments, eventually collapsing into clusters of galaxies. The underdensities are robbed of their contents, becoming vast cosmic voids with densities far below the cosmic average. What began as a gentle ripple becomes a sharp contrast, thin threads of matter outlining enormous, almost pristine bubbles of emptiness. But there is a twist. The first thing to collapse was not the ordinary matter that makes you, me, and every Earth-like world we can imagine. It was dark matter, the invisible mass that does not glow, does not interact with light, but does respond to gravity. Dark matter formed an unseen scaffolding, a three-dimensional skeleton of clumps and filaments. Ordinary gas then fell into this hidden framework, cooled, and eventually formed stars, planets, and maybe even life. In the hunt for alien life, we rarely mention it, but dark matter quietly decided where the habitable islands of the universe could even exist. Optimistically speaking, this process was incredibly efficient at making structure, but also incredibly efficient at making nothing. Most of the matter ended up packed into a small fraction of the total volume, leaving the rest as lonely intergalactic deserts with maybe one atom in a cubic meter. So it's time to find out the truth about this apparent paradox. The same gravity that builds every star and every potential Goldilocks zone is also what drains the vast majority of space, leaving it almost perfectly empty. But why were the initial conditions tuned just right for this web to form at all? And what does that mean inside a single galaxy? Dark energy, the force stretching emptiness, wider gravity, may weave the cosmic web, but what if something else is quietly tearing that web apart? For most of the 20th century, we expected the expansion of the universe to slow down. After all, everything with mass attracts everything else. More matter should mean more breaking. So, let's begin with a surprise that shook cosmology. In the late 1990s, astronomers used Type 1 supernovae, standard candle stellar explosions in distant galaxies, to measure how fast the universe was stretching in the past. The data did not show slowing, it showed speeding up. This was not a small tweak. Those supernovae were fainter than they should have been if expansion were decelerating. The only consistent conclusion? Distant galaxies were farther away than expected because space had expanded more than expected. The expansion of the universe is accelerating, but while gravity works to pull galaxies together, something else is acting on the largest scales to push them apart. So it's time to find out the truth about this invisible driver. We call it dark energy. Not because we understand it, but because we do not. It should be noted that this is really a placeholder name for whatever is causing the acceleration. According to our best measurements of the cosmic microwave background and large-scale structure, about 68% of the total energy content of the universe is this dark energy. Roughly 27% is dark matter, which helps bind galaxies and clusters. Barely 5% is normal matter, everything from every star and planet to every possible habitable Earth-like world we might dream of in the hunt for alien life. So what does this have to do with emptiness? This means that as dark energy drives accelerated expansion, galaxies that are not gravitationally bound to us recede faster and faster. The local group, our small collection of galaxies, stays together, but distant galaxy groups drift away, the gaps between them stretching. The vast voids threaded between cosmic filaments do not just sit there, they effectively swell, becoming larger and more isolated with time. A useful way to picture this is with the classic balloon or raisin bread analogy. Imagine dots on the surface of an inflating balloon, or raisins embedded in rising dough. As the dough expands, every raisin sees every other raisin move away. Crucially, the more distant raisins separate faster than the nearby ones. The raisins are not flying through pre-existing emptiness. Space itself is stretching. Our galaxies are the raisins. The dough is the fabric of the universe. Optimistically speaking, there is still a rich, observable cosmos today. But project this acceleration tens of billions of years into the future. Eventually, almost all galaxies outside our local group will slip beyond our cosmic horizon, receding so fast that their light can never reach us. Future astronomers, living on a planet in a Milky Way, like Island, will look out and see only darkness beyond their own system of stars. To them, the universe will not look almost empty, it will look completely alone. And that raises an unsettling question: how much of our current picture is shaped by the particular cosmic era we happen to inhabit? Binary question: is emptiness our enemy or our only chance? So if our view of the cosmos depends on when we look, we have to ask a sharper question. In a universe this empty, is the nothingness out there our enemy or our only chance? On the one hand, the emptiness feels hostile. Between galaxies, there is, on average, about one lonely atom in a cubic meter of space. Signals from any distant civilization would have to cross oceans of near-perfect vacuum. Even inside a galaxy, stars are separated by light years of darkness. Is that why we feel so utterly alone, despite the sheer size of the cosmic stage? But while the void looks unfriendly, it should be noted that without emptiness, gravity would play a very different game. So, let's begin with a thought experiment. Imagine a universe 10 or 100 times denser than ours. Matter would clump faster, gravity would overwhelm pressure, and clouds of gas would collapse almost immediately. Stars would form in violent bursts, merge, and collapse into black holes. Whole regions might become gravitational minefields, where any fragile planet is either sterilized by radiation or swallowed outright. In the hunt for alien life, that kind of cosmos is a nightmare. Long-lived, stable stars like our sun would be rare. Calm, extended Goldilocks zones where an Earth-like planet can orbit for billions of years might almost never appear. Life would keep trying to start, only to be reset by the next catastrophic merger. Now push in the opposite direction. Picture an even emptier universe, where the average density is far lower than what we measure. Gravity would struggle to pull matter together at all. Instead of a rich cosmic web, we would get a thin mist. Galaxies would be tiny or fail to form, stars would be scarce, and most atoms would drift forever in the dark, never joining a planet, an atmosphere, or a brain capable of wondering about any of this. This means our universe might be a narrow middle ground, just enough matter to weave filaments of galaxies and build long-lived stars, but not so much that everything collapses too quickly. Optimistically speaking, we live in a cosmic sweet spot, a universe that is almost empty, yet just dense enough to assemble islands where chemistry has time to become biology, and biology has time to become us. Seen this way, the Fermi paradox changes flavor. Maybe the universe feels empty of civilizations, not in spite of its vastness, but because the same conditions that allow life to exist also demand that most of space stay barren and quiet. To get a few habitable worlds, you need an ocean of nothing in between. So it's time to find out the truth. Did the universe have to be almost empty for us to be here at all? In the next section, we will connect this strange binary directly to the anthropic principle and fine-tuning and ask a deeper question. Is this apparent sweet spot an accident or a clue? Roadmap from cosmic voids to the space inside atoms. So if the universe really had to be this empty for us to exist, how do we actually see that in the structure of reality itself? Because in this episode, that is exactly what we are trying to unpack together. I am host Name, and this is channel Name, where we take the latest physics and cosmology and ask what it really means for our place in the universe. Today, we are not just listing strange facts about empty space. We are building a roadmap through emptiness, from the largest scales we can map down to the space inside the atoms in your body. So, let's begin with the biggest canvas we have. First, we will zoom all the way out past individual galaxies to the cosmic web itself. Thin filaments of matter surrounding enormous voids that can span hundreds of millions of light years. We will see how dark energy is stretching that web, making those voids grow, and ask why most of the cosmos is not galaxies, stars, or planets, but silent nothing. Then we will step down a level. Inside those filaments, we will look at galaxies that seem crowded in images, yet are mostly vacuum. We will cross a typical solar system, where a star and a few planets are separated by gulfs so large that, on this scale, even Jupiter is a dust mote, and then the pattern will repeat again inside atoms, where more than 99.99999999999% of the volume is empty space. But while this sounds like a simple tour of how empty is empty, that is not our real goal. Our real goal is to understand the mechanisms that carved this emptiness out of an originally hot, nearly uniform fireball. This means asking how gravity sculpts the cosmic web, how quantum rules arrange electrons around nuclei, and whether a universe with less empty space could ever have produced complex chemistry, stars with long stable lives, and eventually beings like us. Pattern interrupt. Imagine the opposite universe for a moment. No great voids, no gaps between orbits, no empty space inside atoms, just a smooth, dense fog of matter everywhere. Could anything like an Earth-like world form there? Could any kind of life even breathe in such a place? Or would it be crushed by its own abundance? It should be noted that we will not stop at the physics. In the hunt for alien life, we usually ask where planets might be habitable. Here, we will flip the question. If the universe is so vast, why does it feel so empty of signals and civilizations? That is the Fermi paradox in the language of cosmic emptiness. Finally, we will connect this to the anthropic principle and fine-tuning. Optimistically speaking, maybe this near-nothingness is not a bug at all, but a feature that selects for observers. As we mentally zoom from the cosmic web down to subatomic space, keep one question in mind at every level. Is all this emptiness an accident, or a clue we have not yet learned to read? Inside galaxies, islands of light in a sea of dark. If the cosmic web is mostly nothing, what happens when we zoom in on one of its bright knots and ask the same question again? Inside a galaxy, does the emptiness finally end, or does it just change scale? So, let's begin with home. The Milky Way is not a solid pinwheel of light. It is a flattened disk about 100,000 light-years across, but only roughly 1,000 light-years thick where most of the stars live. Picture a cosmic pancake, incredibly wide, surprisingly thin. Even inside that disk, the typical distance between neighboring stars is not kilometers, or even billions of kilometers, but several light-years. For our Sun, the nearest star, Proxima Centauri, is over 4 light-years away. That number is so large, it barely means anything to our brains. So it's time to find out the truth with a concrete analogy. If the Sun were a single ping-pong ball sitting in New York City, the nearest star would be another ping-pong ball all the way in Los Angeles. Between them, almost nothing. Maybe a few dust grains scattered somewhere over the entire continent, plus some invisible gas atoms drifting in the dark. This means that what looks like a bright, continuous band of the Milky Way in the night sky is, in reality, a handful of tiny balls separated by continental, even transcontinental, gaps. But while long-exposure images of galaxies look crowded, with thousands of brilliant points packed together, those points are lying to our intuition. Each one is a star system with enormous empty bubbles around it. Even in the densest regions we know, like globular clusters, where hundreds of thousands of stars share a relatively small volume, actual star collisions are rare over billions of years. They are like ships on a vast ocean that almost never scrape hulls. It should be noted that the space between those stars is not perfectly empty. Interstellar space in the Milky Way has, on average, about 1 atom per cubic centimeter. That is already much denser than the space between galaxies, but compared to anything we can build on Earth, it is an almost perfect vacuum. The best laboratory vacuums still contain millions of times more particles per cubic centimeter than the thin air between the stars. Planets, asteroids, comets, even giant gas clouds are tiny specks inside this volume. A habitable, Earth-like planet is a dust mote orbiting a ping-pong ball, adrift in a stadium of darkness. In the hunt for alien life, we often imagine crowded skies and busy neighborhoods, yet even in a galaxy, the supposedly dense part of the universe, most of the real estate is dark, cold, and almost completely empty. So if our bright island of stars is still mostly void, what happens when we dive down another level, into the space inside atoms themselves? Solar systems, vast wastelands between tiny worlds, so if even atoms are mostly empty, what happens when we zoom back out to something familiar, like our own backyard in space? We often picture the solar system as a neat diagram, planets lined up almost shoulder to shoulder, but while those images are useful in school, they are wildly misleading. Our solar system is a case study in cosmic emptiness. On paper, it sounds busy: 8 major planets, dozens of moons, dwarf planets, rings, comets, and an asteroid belt. It sounds crowded, almost like a bustling city of worlds around our star. This means we instinctively imagine that if you flew through it, you would be dodging planets every few minutes. The reality is the opposite. So, let's begin with a simple scale model. Imagine the Sun, shrunk down to the size of a basketball. On that scale, Earth becomes a tiny peppercorn. How far away would we place it? Not a few centimeters, not across the room, but about 26 meters away. That is more than half a basketball court of pure darkness between our planet and its star. Now stretch that same model outward. Neptune, the outermost major planet, would be a grain of sand almost a kilometer away from the basketball Sun. Between the peppercorn of Earth and that distant grain of sand, essentially nothing. A few dust motes of rock and ice separated by oceans of empty space. It should be noted that even the other planets, like Venus or Mars, would be just more specks scattered through that vast corridor. But what about the orbits themselves? Those elegant ellipses we draw look like solid tracks. In reality, each orbit is mostly void. Even the supposedly crowded asteroid belt, often portrayed as a maze of tumbling boulders, is incredibly sparse. Spacecraft like Voyager, New Horizons, and missions to Jupiter and Saturn have all passed through without threading any dangerous needle, because they almost never even come close to an asteroid. If you picked a random kilometer-sized asteroid in the belt and asked, "Where's the next one?" the answer would often be millions of kilometers away. That is more than the distance between Earth and the Moon, just to reach the next lonely rock. In the hunt for alien life, this is a sobering picture, even within a planetary system. Solid worlds are rare dots in a huge black arena. Why is it like this? The emptiness is not an accident, it is dynamically necessary. If planets were packed much closer together, their mutual gravity would twist and tug their paths until the whole system unraveled. Orbits would cross, worlds would collide, and many planets would be thrown into the cold dark between the stars. Optimistically speaking, the space between planets is the price we pay for long-term stability. Wide separation lets a system survive for billions of years, long enough for a small rocky world to cool, hold on to an atmosphere, and maybe become habitable. So it's time to find out the truth behind a deeper mystery. If even our own solar system is mostly empty, and most stars do not host an Earth-like planet in the Goldilocks zone, what does that say about the odds of life in a universe where every larger scale is already dominated by the void? Atoms. The emptiness hiding inside solid matter. So if the vast stretches between stars and galaxies are mostly nothing, we might feel safely distant from that cosmic emptiness. But what if that same nothing is hiding in the most familiar place of all, inside the matter that makes you, your chair, and the device you are watching on right now? Look around the room. Everything looks solid, continuous, reassuring. But while our senses tell us that, the physics tells a very different story. It should be noted that every object you see is made of atoms, and atoms are not tiny hard balls packed edge to edge. They are mostly void. So let's begin with the basic structure. An atom has a nucleus in the center, made of protons, and neutrons squeezed into an incredibly dense droplet. Around it, electrons occupy a cloud of orbitals, regions where there is a probability of finding them as they zip around the nucleus. Between that dense core and the electron cloud, almost nothing. No extra particles quietly filling the gap, just space. How empty is that space, really? Imagine we scale up a single hydrogen atom. If we let the nucleus swell to the size of a marble placed at the center of a huge sports stadium, where would the electron be? Somewhere out near the outer seats, in a vast, ghostly cloud. Everything between the marble and those seats, all the volume of the stadium itself, would represent empty atomic space. This means that over 99.99999999999% of the volume of an atom is emptiness. The numbers are so extreme that they almost stop feeling real. But they have a startling consequence. If we could somehow remove all the empty space inside the atoms of a human body, compressing just the nuclei and electrons together, your entire mass would shrink to something smaller than a grain of rice. Pattern interrupt. That grain of rice would still weigh the same as you do now. Can we really call ourselves solid when our apparent solidity is built on such a fragile scaffold of almost nothing? In the hunt for alien life, we usually think about planets in a Goldilocks zone, about whether an atmosphere can stay stable, about how far a world orbits from its star. But the possibility of a habitable, Earth-like planet depends on chemistry, and chemistry depends on atoms having this strange, mostly empty architecture. If atoms were tightly packed little cubes, would complex molecules, cells, and eventually life even be possible? So it's time to find out the truth about emptiness. The universe is not just empty between galaxies. Emptiness is baked into the very blueprint of matter itself. Is that a cosmic coincidence, or is a universe dominated by nothing the only kind in which something like us can ever arise? In the next part, we push this idea out to the largest scales of the cosmic web, the Fermi paradox, a silent universe in a sea of space. On the largest scales, we saw a cosmic web, thin threads of matter wrapped around enormous voids. But there's another kind of void that might be even more unsettling. If the universe is sprinkled with planets and stars, where are the minds? Where is everybody? This question has a name: the Fermi paradox. Given hundreds of billions of stars in our galaxy and hundreds of billions of galaxies in the observable universe, it seems almost inevitable that some worlds should host intelligent life. We know that Earth-like planets are not rare. We know that stars live for billions of years. In the hunt for alien life, the numbers look wildly in our favor. So why does the sky sound so quiet? Our radio telescopes have been listening for decades. We have surveyed millions of stars, scanned whole patches of sky, and searched for artificial patterns in the data. Yet we have found no unambiguous technosignatures, no clear sign of a transmitting civilization, no obvious megastructures reshaping the light of a distant star. It should be noted that this does not prove we are alone. But while the universe is huge, our results so far are a very precise kind of nothing. This means the physical emptiness we have been talking about is not just a backdrop. It actively makes the problem worse. Even if a planet around some distant star does grow a technological species, the vast distances between systems, combined with the finite speed of light, turn the galaxy into a maze of isolation. A simple radio signal from a world 1,000 light-years away would take 1,000 years just to say hello, and another 1,000 to hear hello back. Across Across galaxies, communication is so slow, it is almost the same as silence. Space is not only mostly empty, it is also expanding. As dark energy stretches the cosmic web, many galaxies are receding from us faster than light, not through motion, but because the space between us is growing. Any signal they send today will never arrive. Optimistically speaking, there could be countless civilizations out there, each trapped inside its own shrinking island of visibility, like ships on an ocean whose waves are pulling them apart. So, let's begin to think about a more disturbing possibility. Maybe there is a cosmic filter that very few civilizations pass. Perhaps the same conditions that make the universe structurally possible, low average density, long-lived stars, gentle expansion, also conspire to keep technological species rare, short-lived, or forever confined to their local system. Is the emptiness simply giving life room to grow, or quietly preventing it from ever connecting? So it's time to find out the truth about a different kind of nothing. Maybe the universe is not just physically empty, but informationally empty as well. In the next part, we will ask whether a cosmos this sparse is an accident or the only kind of cosmos in which observers like us can ever arise to notice the silence. Anthropic principle? Did emptiness choose us? What if the universe had to be almost empty just so that someone could be here to complain about how empty it is? We are used to asking, why is it like this? But there is a quiet, unsettling reply, because if it weren't, you would not be here to ask. That idea has a name, the anthropic principle. In simple terms, it says that when we look at the cosmos, we are not seeing a random sample of all possible universes. We are only seeing a tiny subset whose conditions are compatible with observers. This means our view is biased from the start. We do not live in a universe that is typical. We live in a universe that is survivable. So, let's begin with fine-tuning. Cosmologists have noticed that many of the fundamental numbers that set the stage for everything, the strength of gravity, the amount of matter, the value of dark energy, seem delicately balanced. Change them slightly, and you do not just get a different kind of planet or star. You get a universe where structure never forms, or one that rips itself apart. Take gravity and the overall density of matter. If there were much more matter packed into the same space, gravity would be stronger on cosmic scales. The early universe would collapse on itself before galaxies could settle, where it might fragment into violent, dense clumps and black holes. Long-lived, stable stars like the Sun would struggle to exist in that chaos, and with them, the slow chemistry that leads to life. But if there were much less matter, the opposite disaster plays out. Space would expand, almost unhindered. Tiny ripples in the early plasma would never grow into galaxies. No filaments, no clusters, no cosmic web, just an ever-thinning fog of particles. Too smooth for planets, too smooth for biology. A universe that is not just empty of visitors, but empty of any place they could ever arise. Our universe seems to sit in a narrow middle ground. On average, there is only about 1 atom in a cubic meter of intergalactic space, almost perfect nothing. And yet gravity has just enough time, and just the right competition with dark energy to pull that almost nothing into the cosmic web, thin chains of galaxies wrapped around enormous voids. Inside those galaxies, some stars are quiet, long-lived, and stable. Around a few of those, small rocky worlds can orbit in a Goldilocks zone, with atmospheres, oceans, and complex chemistry. Optimistically speaking, that is where life gets its chance. It should be noted that this picture raises a deeper question. Are we uncovering a profound law that demands an almost empty cosmos, or are we simply noticing that only in this rare, sparse kind of universe can anyone evolve the tools to notice anything at all? So it's time to find out the truth about how far this logic goes, and whether emptiness itself might be selected, not by design, but by survival. Uncertainties, what we still don't know about nothing. So, let's begin with an uncomfortable admission. For all the confidence we sound like we have, a lot of the emptiness in the universe is built on things we do not really understand. And at the top of that list sits dark energy. We say dark energy is stretching space, making the cosmic voids grow, pushing galaxies apart faster and faster. But what is it, actually? It should be noted that right now, we have options, not answers. It might be a true cosmological constant, an energy built into space itself. It might be a new kind of field, gently rolling in the background of the cosmos. Or, it might be telling us that our theory of gravity, which works beautifully for planets and stars, quietly breaks down on the largest scales. This means even our story of why the universe is becoming more empty could be missing a crucial chapter. Our maps of that emptiness are also far from complete. When we show you the cosmic web, with bright filaments and giant voids, it looks like we have the whole layout. We do not. We only see as far as light has had time to reach us, a bubble about 46 billion light-years in radius. Beyond that horizon, the structure could be different. Even inside it, there are huge regions of sky, where our galaxy surveys are shallow, or blocked by dust, or simply not done yet. Imagine trying to judge an entire continent by a few cities lit up at night. That is the level of bias we are fighting. Then, there is life. In the hunt for alien life, we talk about the habitable zone, about Earth-like planets with the right orbit and the right atmosphere. But all of that is based on one example: Earth. We do not know how flexible life really is. Could it thrive in subsurface oceans under ice, in thick hydrogen shrouds, or in environments we would never call Goldilocks? When we estimate how many civilizations might exist, we are extrapolating from a single data point, which is statistically almost nothing. Here is the pattern interrupt. The next few decades could rewrite this entire picture. Next-generation galaxy surveys will trace the cosmic web more precisely, testing whether dark energy behaves exactly as expected. Gravitational wave detectors will let us weigh invisible structures and probe gravity itself across billions of light-years, and telescopes searching for biosignatures and technosignatures will start telling us whether apparently empty planets and systems are truly lifeless or just quiet. Optimistically speaking, a single clear detection of life, or a small deviation in how space expands, could flip our understanding of how empty the universe really is. So it's time to find out the truth about our own ignorance. Uncertainty does not weaken this story, it is the story. The fact that we can measure the vacancy of intergalactic space, argue about dark energy, and seriously search for faint traces of life across the sky is already extraordinary. The next step is to ask whether this vast emptiness is permanent, or whether, given enough time, it might be filled with something new, or with someone new. Reframing emptiness, lonely void, or cosmic opportunity. If almost everything is nothing, what does that say about us? In the hunt for alien life, and even for simple meaning, that question might be the most important one we can ask. So, let's begin by retracing the path we have taken. We started with the cosmic web, delicate filaments of galaxies stretched across unimaginable distances, wrapped around giant voids like the Buta's Void, where hundreds of millions of light-years contain almost no galaxies at all. We followed dark energy, quietly pulling the fabric of space apart and making those voids grow. We dove into sparse galaxies and even sparser solar systems, where the average distance between stars is trillions of kilometers. Then, we shrank down into atoms, where more than 99.99999999999% of the volume is empty space, and finally we asked what this all means for life and for us. At first glance, it feels like a cosmic insult. Why build a universe that is almost entirely empty? But while it looks wasteful, this emptiness is not a mistake. It is the stage on which everything else is possible. Without huge regions of low density, gravity could not slowly sculpt the cosmic web. Matter would collapse too quickly, stars would burn too fast, and long-lived stable systems like our own would be rare or impossible. The same is true inside atoms. If protons, neutrons, and electrons were jammed together with no space between them, there would be no flexible chemistry, no complex molecules, no solid planets, and no Earth-like environments. This means the nothingness between particles is exactly what allows an atmosphere to form, water to flow, and biology to experiment. So how should we feel about all this? Is the universe a lonely void or a careful arrangement? On one hand, the silence can be crushing when we remember that there is, on average, about 1 atom per cubic meter in intergalactic space. Our entire lives start to look like a brief flicker in an infinite dark. But while the emptiness can feel isolating, it also throws every pocket of light and warmth into sharp relief. Every star, every habitable planet, every conscious mind becomes not just ordinary matter, but an extraordinary exception. It should be noted that our sense of cosmic loneliness may itself be temporary or even misleading. We have only just begun to map the sky for radio signals, to analyze exoplanet atmospheres, to search systematically for technosignatures. So it's time to find out the truth about whether the silence is real or just a symptom of our technological infancy. Optimistically speaking, the most astonishing fact may be that anything exists at all, and that some of that anything can look up, measure the void, and ask why. In a universe where almost everything is nothing, what could be more precious than a place and a time where something has learned to wonder? But if emptiness is a precondition for structure, could it also be a resource, something future civilizations might learn to shape, or even escape? Closing thoughts and call to action, your place in the empty universe. If emptiness is a resource, what does that make us? In a universe where almost everything is nothing, we are part of the tiny fraction that is not. So let's step back one last time and look at the whole picture. From the vast intergalactic voids, with barely one lonely atom in a cubic meter, to the space between stars and planets, all the way down to the mostly empty interior of each atom in your hand, the pattern is the same. The universe is overwhelmingly empty at every scale. This is not a mistake in the cosmic design. This means the same laws that stretch space, that let gravity sculpt galaxies, also demand that most of reality is silent, dark, and sparse. But while the early universe was hot, dense, and almost uniform, the one we live in now is anything but. Gravity gathered matter into a delicate cosmic web of filaments and clusters. Expansion pulled those filaments apart. Dark energy then took over, accelerating that expansion and deepening the voids between them. The result is a universe where galaxies are rare islands of light, separated by oceans of almost pure nothing. It should be noted that without that emptiness, those islands would never have formed, and worlds like Earth would never have cooled enough for life. So, when we ask, why did a dense beginning turn into such an empty cosmos, the answer is simple and strange at the same time. The universe did not choose emptiness. Emptiness is what you get when you let gravity, expansion, and dark energy run for billions of years. Optimistically speaking, it is exactly this balance that makes a habitable planet under a stable star even possible. Now that you have seen how empty things really are, how does it feel? Does the scale of the void make you feel more alone, as if our tiny world is lost in an endless black ocean? Or does it make you feel more special, knowing that in the hunt for alien life, conscious observers of any kind may be incredibly rare islands in an almost featureless sea? Tell us in the comments. Does the emptiness make you anxious, peaceful, or inspired? Share your own analogies for cosmic scale and nothingness. If you have ideas for future deep dives into the structure of reality, from dark energy and the ultimate fate of an ever emptier universe, to whether any civilization could ever cross the gulfs between these islands of light, we want to hear those too. So it's time to find out the truth about how you see your place in this almost empty cosmos. If you enjoyed this journey, subscribe, stay with the channel, and keep exploring with us. Because as long as there is at least one small patch of universe asking questions, the void is not all there is.